Hi doctor, I'm Lim Bing Sheng. I'm going to present DMA, which is Dynamic Mechanical Analysis. The objective is to characterize the mechanical properties, stiffness, damping, and viscoelasticity of materials, and then to produce graph of storage modulus E prime, loss modulus E double prime, and tangent delta against temperature or frequency or strain amplitude sweeps. And in temperature sweeps, it is important for analyze the glass transition. Here's a diagram showing that some DMA machine. The component of DMA consists of drive motor or force generator, which generate force in constant or in frequencies, and then a load cell, which measure applied force or stress or pressure, and displacement sensor, usually LVDT detector, which measures strain, which is distance, and then sample clamp to hold the sample, temperature control system, a furnace or liquid nitrogen cooling, thermocouple measure temperature, computer to calculate E prime, E double prime, tangent delta. Delta is a phase difference of stress and strain. For the instrument working principle, first one is the force generator. It is a electromagnetic actuator, which is also called voice coil, and it is similar to a speaker, but it looks like this cylindrical shape. This load cell is to measure the stress or the pressure applied on the material or the sample. It is sensitive to left right and then insensitive to up down. Then you can put this in a something, for example, put in the something, it will be compressed, and then it will compress the sensor, and then the resistance will be changed according to the distance, the length it compressed. For LVDT, it is to measure the distance, and then it consists of primary winding and secondary winding. The primary winding is to produce the AC magnetic field, and then the secondary winding is to receive the magnetic field. And then it measures the difference between the first and the second secondary winding to determine the position of the soft iron core. Here shows how it moves when the soft iron core is upside, and the first secondary coil have a higher received magnetic field, and then it will have generated larger current or voltage, and then the downside secondary coil will have smaller voltage, then the larger one will counter the smaller one, and then the voltage will go downside. For the second picture, the soft iron core is on the downside, so the downside secondary coil will receive more current, and then it will force the smaller current on the upside secondary coil. It cancel off the upside one and then go in the upside, and then upside here got larger voltage, and it is sensitive to the displacement of this soft iron coil, so it can be used in DMA. DMA got different operation modes. In general, it got tension, compression, bending, shear, and torsion. Here's two diagrams showing how the different modes operate. And then DMA is no need vacuum because the air damping effect is negligible compared to material damping. Here's showing a most versatile DMA in the world, which is DMA 242E Artemis. Here's some parameter of it. Its control force range is 24 Newton, static travel range of 20 mm, frequency range from 0.01 to 100 Hz, and sample holders larger than 30 type. And here's another technical specification of it. Then for the physics working principle, so this is the three parameter DMA measures. First is elastic response, which is storage modulus, and then viscous response, loss modulus, and damping loss factor. This tree is plotted on y-axis. Here's the diagram showing these three parameters in the glass transition temperature. This diagram showing that the relationship between loss modulus and storage modulus. First, loss modulus is measure the viscous response, and then storage modulus is measure the elastic response. So when the ball is hitting the ground and then reflect back, where it hits the height, it is the storage modulus, the elastic part, and then what it lost is the viscous part. This diagram shows how the DMA really measure that three parameter, and it is first measuring the stress and the strength from the load cell and the LVDT. First, to obtain the stress, it is from the stress formula is force over area. The force is from the load cell, and then the area is the cross-section area of the sample. For the strength, the L length of the sample is obtained, and then the delta L is obtained from LVDT, which is the change of length is from LVDT. From the diagram, here shows the stress is lead the strain. Why the stress is lead the strain is because when we apply the force, then only the material will change shape. So the material will change in length after apply the force. So the length always is lagged by the force. If it is very viscous, then the length will lag more. If it is very elastic, then the length will lag lesser. Then how much the phase lag will be in maximum and minimum, it is from 0 to 90 degrees. The input and output, the formula stress and strain, we add sine omega t is because this is a wave. And then for strain, we minus the delta, which is the phase difference of stress and strain. And after that, we use these two parameters, stress and strain, to divide from stress divide strain, and then we obtain the real part and the imaginary part. And for the real part, we got the elastic, which is the storage modulus E prime, and then the imaginary part, we got the viscous part, which is loss modulus E double prime. And then for the tangent delta, we divide the loss modulus by the storage modulus, and then sine delta over cos delta, we obtain tangent delta. And then the stress and stress over strain cancel off. For an ideally elastic material reacts immediately without any delay. The sinusoidal stress and strain curve show no phase shift, thus delta equal to 0. This shows in the first diagram. Second, the stress and strain curve of an ideally viscous material show a phase shift angle of 90 degrees, which shows in the right side of the picture. And as the term viscoelasticity suggests, the behavior of viscoelastic materials is a mixture of the two. Thus, the phase shift angle is from 0 to 90 degrees. For the x-axis, which we call sweeps, we got temperature sweep, frequency sweep, and amplitude sweep. The most famous one is the temperature sweep, then comes to the frequency sweep. And the other is more uncommon, and yeah, these others got temperature ramp, humidity sweep, and time sweep. The time sweep, maybe we put the sample there over some time and let it erode or something else. It will change in the material itself over the time, like the material become rusty, for example. For the temperature sweep, the frequency and amplitude is constant. The amplitude is the length, the strain applied, or the stress applied, and usually is the strain applied, and it's constant. Frequency is constant, usually using 1 Hz for temperature sweep. And then here 1 to 5 degrees Celsius per minute of temperature change. Usually the temperature swap will use. This is the temperature ramp or the temperature change rate. And the most important part or the most famous we investigate is the glass transition region. Glass transition temperature Tg is a specific temperature range for each amorphous material like plastic, glasses, rubbers, where it changes from a hard, brittle state to a soft, rubbery one. Then we come to frequency swap. The temperature is constant, amplitude is constant, and then the change is only the frequency. We get at least 5 to 10 full cycles for each frequency for a reliable modulus measurement. We need to measure the phase change between this stress and strain. So we obtain 5 to 10 full cycle to measure it averagely or taking the effective part of the measurement. And then here is the graph after convert it from the stress and strain. Here's another example of frequency swap. And then for amplitude swap, the temperature is constant and the frequency is constant. Then left amplitude is changed. Usually we force the distance, not the force in the force generator. And from the graph, we can see the storage modulus and loss modulus is constant over some distance, which this distance is called LVE range, which is linear viscoelastic range. And then after it is called non-linear viscoelastic range. Then the storage and loss modulus will falling. And then the right part diagram showing the force generator amplitude. It is going higher and higher. As it goes higher, the storage modulus and loss modulus is dropping down. This shows the material is deformed. Here's the example from first journal paper. The title is Engineered Elastometric Bio-Nanocomposites from Linseed Oil or Organoclay tailored for vibration damping. The method in DMA used is Perkin-Elmer DMA 8000, and then the sample size is 10 times 5 times 2 mm in the mode of strain controlled compression mode, and it measures under 1 Hz frequency, and then the dynamic strain of 0.01%, which means the length of the sample versus the strain it changes. The temperature range is from negative 30 degrees Celsius to 60 degrees Celsius, and the rate of increase at 5 degrees Celsius per minute. And then it also measures the frequency swap. Here the mode it uses is also same compression mode, and then the dynamic strain of 0.0005%, which is smaller than the temperature swap. And then the frequency range is from 1 Hz to 50 Hz. Then the temperature is constant at 25 degrees Celsius room temperature. Here's a graph showing that the storage modulus and the loss factor. Here the loss modulus is unsure because we can get from the loss factor and storage modulus by multiplying storage modulus and loss factor. Here the diagram shows the 0% weightage of the clay is much lower, and then 1% weightage is higher, 4% weightage is the highest storage modulus, and this is the glass transition region of the clay. Now we see the loss factor. The 0% weightage is the highest, and then the 4% weightage is the lowest. And then this is the conclusion it gets from the graph upside, and the temperature is negative 30 degrees Celsius. It has highest storage modulus. For higher temperature, which is 50 degrees Celsius, it has lowest storage modulus. Here is the result for frequency swap. We can see the 0 weightage is always the lowest one, and then the 4% weightage is the highest one in both storage and loss modulus. and then we focus on the loss factor. For the 0% is highest, and then 4% is lowest, and it comes to the conclusion which the 0% is highest and the 4% weightage is the smallest loss factor. For the summary of the result, for the storage modulus, it increases with clay content, which nanoclay reinforces polymer, improves rigidity and thermal stability. Loss modulus and tangent delta, peak indicates primary relaxation. Tangent delta, it decreases with clay, more elastic behavior at higher frequency. Temperature effect, E' drops sharply near transition temperature, glass transition temperature, then forms rubbery brittle, effective damping tangent delta larger than 0.3, observed at 39 to 87 degrees Celsius. Frequency effect, E' and E" increase with frequency. Tangent delta slightly decreases. Material becomes more elastic. Overall conclusion, nanocomposites show improved stiffness, stable damping, and suitable viscoelastic properties for vibration or noise control over a wide temperature and frequency range. The example from the second journal paper for the title is Influence of Moisture Content on the Thermal and Mechanical Properties and Curing Behavior of Polymeric Matrix and Polymer Concrete Composite. For the method, the samples for mechanical testing were made 24 hours after the start of curing, which was conducted at the ambient temperature. And then the DNA was conducted using a TA instrument SDT2960 USA instrument. The setting of the device through frequency sweep and for dual cantilever, and to test for tangent delta and storage modulus. The sample size was identical to the mechanical test, which is 50 × 10 × 2.5 mm. This is the result they get, the graph. When the frequency higher, the storage modulus getting higher. At higher frequency, it is more elastic. And then for 0% water, the elastic is more higher. For the tangent delta, here shows inwardly, which the 0% water is lowest. Then this result indicates that the storage modulus declines and the damping factor tangent delta increases for the resin as the water content increases. This may be due to the increase in microcracks and voids with increasing water content in the resin. Here is a reference, and thank you for your attention.